Okay. I think I might have gone too far. Okay, the first thing we're going to talk about is derivatives of exponential functions. There are two kinds of exponential functions. Both of these kinds of functions are numbers, constants, and the variable is the power. So you don't do power rule on these. When the variable is the power, you have what's called an exponential expression. So you don't subtract 1 from the variable and drop the variable down in front. Don't confuse it with power rule. As long as you don't confuse this with power rule, you're going to be fine. Because the rules themselves are actually really easy. The derivative of e, which is the natural logarithm of 1, the derivative of e raised to the x power is e raised to the x power. It is its own derivative. The reason that it works that way is actually explained by the other exponential derivative rule, which says that if you have any number besides e, call it a, or b, or whatever you want to call it, but if you have any number other than e, and raise it to the x power, the way that you take its derivative is you take the natural logarithm of that base and multiply it times that number raised to that power. It's also its own derivative, except that you have to include the natural logarithm of whatever the base is. The reason that you didn't actually see that happen in the derivative of e to the x is because the natural logarithm of e is equal to 1. Okay? So what this is really saying is this is really the derivative of e to the x is the natural logarithm of e times e to the x, but because the natural logarithm of e is 1, 1 times e to the x leaves us with just e to the x. So we didn't actually need to put down the natural logarithm of e. But for any other number, you take the natural logarithm of whatever that number is, and then multiply it times that number raised to the power. And the power is the variable. So the derivative of an exponential function is the original function times the natural logarithm of whatever the base was. Now, that is not to say that it always is quite that straightforward. Since the variable is in the power, it is entirely possible that that power may be an expression of x, like 2x squared plus 3, which then is going to make that power turn that whole problem into a chain rule problem. But remember, all you do when you have chain rule is you always, at the end, whatever the inside function was, you tack its derivative on to the end of the problem. So we're going to do some examples where that happens. The other thing that can happen is that you can have either one or both of these as a factor in a two-factor product problem, or as a numerator or denominator of a quotient rule. All the rules work together. But as far as actually taking the derivatives of exponential expressions, the rules for taking those derivatives are even easier than taking the derivative with a power rule, because they are practically their own derivatives. They don't really change very much. So let's do some examples, and that's the reason that I put the rules on the board, and I did the same thing for the next section, which is going to be when we talk about logarithmic functions. We'll have a log base a function, and then we'll have a natural log function. And these are just inverses of each other. And if you notice here, when we come to the next set of rules, the derivative of any base logarithm of x is going to be 1 over x, and you're going to take the natural log of whatever that base is, just like you took the natural log of this base. It's just that it's going to go down and follow the x into the denominator. And in the case of it being the natural logarithm of x, that's a base e logarithm, and you're going to be taking the natural log of e, which is 1, so that means there's just really a 1 sitting there in front of that x, and you're not going to need to write it down. A natural logarithm is a special logarithm that shows up a lot in business and finance and scientific applications. E is just simply an irrational number, and it is the base that if you raise it to the 0 power like anything else, anything to the 0 power is going to be 1, but because of the properties of exponentials and logarithmic expressions, what that means then is that e to the first power is going to actually give you what the value of e is. And it's a never-ending decimal. And it's actually stored on your calculator. You don't have to worry about figuring out what it is. We're just going to use it in its exact form. So if you're needing to find out what e is, second ln, a natural logarithm is base e. E is the base of the natural log. So if I ask for e raised to a power, if I want to know the value of e, notice here it gives me a big long, and it's a patterned decimal. It's a repeating decimal, but it isn't a perfectly repeating decimal. It does have a repeating pattern in it. That 2.7 kind of throws it off because after that, it's 1828, 1828, 1828, 1828 forever. But it's just a number. Just like pi is just a number. Okay, there are a lot of irrational constants that come up a lot, and we don't always know why they do. It's just that we notice that they do. So if I need to find a base 10 logarithm, I use log. But if I need a base e logarithm, that's called the natural logarithm. So that's log base e. Okay? And again, all you're doing with any of these is they're just numbers. Taking a logarithm is undoing the process of having that number being raised to the x power. So let's see how we can work these problems with just some examples first. Okay, find the derivative of this function. The function is y equals e to the 5x. It follows the pattern of e to the x. So the derivative of e to the 5x starts out by being simply e to the 5x. You always just copy the function right on over. But since the power is not just x by itself, that power actually has a derivative, so it becomes chain rule. The power is an expression, not just an x. So I need to take the derivative of that expression, and the derivative of 5x is 5. So I put a 5 in front of it. Okay? There's the chain rule. Now, I'm going to stick with this one example and do some variations on it before I move on. If this had been y equals e to the x squared plus 3x power, okay? That's just e raised to some power. So again, y prime starts out with what you started with, e to that power. Just copy it over. But because this is an expression, because it's not just x, which would have had a derivative of 1, and then derivative of 1 doesn't change anything. This actually has a derivative that's not 1. So the derivative of this is 2x plus 3, and I can either leave it that way, or I can write 2x plus 3 times e to the x squared plus 3x. Both of them are perfectly correct. There's no difference, because all it is one's multiplying times the other.
So you could write it those three different ways and they'd still be correct.
Yeah, you can write it either way. It'd still be correct. You could try multiplying it out and say it's 2x e to the x squared plus 3x plus 3 times e to the x squared plus 3x, but that's just more trouble. Okay? I wouldn't simplify it out. I would just leave it in those two pieces. But it doesn't matter the order the two pieces come in.
So, like in y equals e 5x, if it's just got one variable, prime would be 5e, 5x.
Exactly.
If it's got two numbers and letters, variables.
If this had simply been y equals e to the x, remember that's equivalent to y equals e to the 1 times x, right? Which would be, for its derivative, y prime would be e to the 1 times x times the derivative of 1x, which is just 1. And we don't need either one of those ones, so we just don't write them down. Okay? So we're really following the same process all the time. It's just that when the number that's up there is 1, we just, 1 disappears on us. We don't really need to write it down all the time. Okay? Now, before I leave this one, because this one is fairly simple, I don't want to complicate things. Before I leave this one, let's try one more that's just a variation on the same thing. What if it's y equals e to the square root of x power? What's the first thing to taking the derivative? What's our first step? Okay, well that means what I want to do is call this e to the x to the 1/2 power then. But when I go to take its derivative, what's the first part of its derivative? It's the same thing you started with. Okay, that's always the first step when doing exponential derivatives, is you start out with what you had. So you start out with whatever that first step was. You just copy it over. But then, because the derivative isn't just x by itself, x actually is being used as a function of some kind, then what we do in this case is, and in this one we would have to realize it was x to the 1/2, so we're going to have to multiply this times 1/2 for that 1/2 power, right? But x to the 1/2, that isn't its whole derivative. The whole derivative of x to the 1/2 is 1/2 x to the 3/2 power. So if I'm going to do this, I probably don't want to use this form at all. I probably want to stick to this form so that I can actually do something with it. So my y prime is going to be more easily written if I call it y equals e to the x to the 1/2, just copied it over, times 1/2 times x to the 3/2 and leave it alone. I'm sorry, not 3/2. It's 1/2 minus 1. It's minus 1/2. Sorry. Sorry. Because I subtracted 1 from it. I didn't add 1 to it. Okay? Now, it doesn't look pretty, but it doesn't have to, because that's all we need to do. Don't do extra steps. You want to rearrange it, you can put the 1/2 x to the negative 3/2 power or negative 1/2 power in front. You write those in either order you want to. I don't care which order you write them in. It's still right. Okay? This one is not e raised to a power. That means there's going to be a natural logarithm involved in the derivative. So s prime is going to be the natural logarithm of whatever the base is, times what you started with. And even if you took the derivative of t, if you tried to do a chain rule on it, the derivative of t is 1, and 1 times ln 3 times 3 to the t is still the same thing what you got right now.
So that's the final answer?
That's the final answer. You're done. Okay? Along the same token, you just pull in whatever the base is, you take its natural log. Okay? So if it's r is equal 3 raised to the t squared power, r prime is going to take 3, take the natural logarithm of it, keep the 3 to the t squared power, but because that's a t squared power, the derivative of the power is 2. You're really taking the derivative of the power every time. It's just that if all there is the variable, the derivative of just the variable is 1. Okay? Yes?
You take the derivative of t squared, right, and put it in front or behind. You're just multiplying it by.
Oh, wait, and yes, and I just realized I left out the t, because the derivative of t squared is not just 2, it's 2t. Yeah, 2t. I just realized that I thought about it, but I forgot to write it down. Okay? That's 2t, which is the derivative of the t squared power, times the natural log of the base, which is ln 3, times what you started with, 3 to the t squared power. Okay? Let's try one more variation on this before we move on. Z is equal to 5 raised to the power t plus 1 quantity squared. Your power has to have its derivative taken of it. What's the derivative of t plus 1 quantity squared? Well, the derivative of t plus 1 is 1. No, you're right. You're right. But you've got to do something about that parentheses, because that's chain rule. Okay? Okay? So the derivative of your t plus 1 squared is going to be 2 times t plus 1, and And 2 minus 1 is 1. And then the derivative of t plus 1 is 1 times the natural logarithm of 5. And then just copy this back over. Now, there's a lot more there than what you actually had to write down, because I didn't have to write down that second 1. You know that the derivative of t plus 1 is 1, but it didn't change anything. So that is the derivative. It's there. So you could leave that part out and say this is 2 times t plus 1 times the natural logarithm of 5 times 5 to the t plus 1 squared power. Now, if you wanted to multiply all that out, you could do that too, but you don't have to. Because 2 times t plus 1 is 2t plus 2. And then you can multiply the natural log through all of that too, but you don't need to. You can just leave it as factors. They don't want to ask a question before we do anything else. I'm trying to present you with the simplest cases, but still make you aware that chain rule didn't go away. Chain rule's still there. Now we need to think through this one. Is that a product? Because I want to make sure that you don't try to do a product rule when it's not a product. Is that a product? No, that's one single term. That 10 is just a number in front of e raised to some power. All that 10 is a multiplier. It's a coefficient. And coefficients, when you take derivatives, coefficients are nothing but hitchhikers. They just follow you right along. Okay? They ride along. So, y prime, keep your 10. Take the derivative of e to the 3x squared, which means keep e to the 3x squared. And then take this whole thing, and I'm going to multiply it by the derivative of 3x squared. I'm going to make it explicit what I'm doing. That's not a step you would have to write out, but I'm trying to make it explicit where the next step comes from. Okay? The derivative of 3x squared is what? 2 times 3 is 6, x to the first, so it's 6x. This drops down without changing. You're done. You don't need to do anything else. You don't need to rearrange it. You can, but you don't have to. Anybody need to ask a question? Something you don't see where it came from or why I did it the way I did it. Same process over and over again. If the power is a function, chain rule says take the derivative of the power and include it as a factor of the derivative of what you started with. That's the only extra step. I didn't show you the slide that had the formula for doing it on there because when people look at it, they go, oh my God, that looks horrible. It's easier to show you how to do it than it is to show you a formula for doing it. Okay? I see a multiplication sign. Is that really a product rule? No, because that H is just sitting there as a coefficient. What's the base of what we're taking the derivative of? No, because you have to apply powers before you can multiply. Remember? Parentheses, exponent, then multiply, divide. So that's 10 times the quantity 10 raised to the 1 over t power. Okay? You can think of that as being this way, if you want to. That might make it easier to think of. What is 1 over t? How can we rewrite that so that we don't have to worry about what to do with it? What do we need to do not to have a fraction? What's another way to write 1 over t? T to the negative 1. Exactly. Exactly. Because it's late and you're tired. Okay? I didn't have any rules that I could use to be able to do the derivative of 1 over t. But if I write it as t to the negative 1 power, I have a rule I can use. I can bring the power down in front and subtract 1 from it. So, hitchhiker. Just bring it down. That's all you ever do with a constant multiplier out in the front. Just bring it along. I need to take the natural log of the base. Because this is not a natural log to start with. This is a base, a regular number as a base, not e. So I need to take the natural log of the base. Then I need to repeat what the original function was. And then my last step is to take the derivative of that power. And that's going to be negative 1 times t to the negative 1 minus 1 power, and you're finished. Now, you probably don't want to leave that as negative 1 minus 1, and you probably would have done this in your head. Yes, it says negative 1t to the negative 1 minus 1 will be negative 2 power. Well, I'm just trying to show you that what you're doing is you drop your power down in front and then you subtract 1 from it. That's the power rule. Okay, that's your power rule. Most of the time you do this part in your head. But just to make sure that everybody remembers this power rule, you're bringing it down in front and then you're subtracting 1 from it. There's the power rule. Everything else stays exactly like it was. And you can rearrange it in any order you want to, but you still have to have all those factors. And if all you're going to do at some point is plug in a number for t, there's no point in multiplying anything out. Just plug in t and plug it all in the calculator. Okay? It's next week. Next week. Yes, we want it fresh. In fact, I will post a practice test for you, and it will be a practice test that I will give you the answer key for, like last time.
You've already got on there you've already got...
Out of the book.
Yes.
And they're answered in the back of the book, but I'm going to post a set of answers that is the first step, because the answers in the back of the book oftentimes are all the extra stuff that there's no need for. So I'm going to actually post the test. I'll post the practice test completely worked out for you.
Oh, so
okay.
That's what you're doing?
Yes.
Okay.
So I'm giving you, the practice test is actually already there. The answers to that practice test are in the book. They're in the back of the book. But because I know they simplified a lot of those answers, you may not recognize it as being what you have. So I'm also going to post the steps to it, not just the answers. Okay? And then I'm going to highlight, this is where you can stop.
Thank you.
Okay.
I thought you were giving us two practice tests, though.
No. It's already there. It's already there. But I was just trying to let you know, I'm going to give you the full, complete answer, not just what's in the back of the book. I'm going to give you the worked out solutions this time because I think you need those.
Thank you.
Okay. Does anybody see a product here? There is. This time we actually do have a product because it is e raised to the x squared plus 1 power times the square root of the quantity 5x plus 2. So there's two factors. And I'm going to go ahead and rewrite that second factor without a radical because I don't have rules that deal with radicals. So yes, we do indeed this time have product rule. We have a product rule. So when you have product rule, you take the factor of each factor and take its derivative. So the derivative of factor 1 I'll call that f prime 1 is the derivative of e to the x squared plus 1. So the derivative is going to be e to the x squared plus 1 times the derivative of x squared plus 1, which is 2x plus 0, and there's no need for me to write the 0. Okay? Then I need to take the derivative of the other factor, factor number 2. Here's its derivative. That's a power rule problem. A power rule with a chain rule, because we've got a 1/2 power on the outside and an expression on the inside. So I bring the 1/2 down in front of the parentheses. I keep what's in the parentheses. I subtract 1 from 1/2. That gives me negative 1/2. Then I need to take the derivative of what was inside the parentheses, and the derivative of 5x plus 2 is 5 plus 0, which I'm going to keep as 5. And then I'll plug the original expression back into the parentheses. So because this is product rule, not power rule. This is product rule, then y prime is going to be the sum of two things. It's going to be the sum of factor 1 times the derivative of factor 2, which is right ugly, but that's still what it is. And I think I will take 5 times 1/2 and call that 5/2 just to eliminate a set of parentheses. So there's the first part. And then I know I have to add. And then factor 2 is 5x plus 2 to the 1/2 power. And I need to give it the other factor's derivative. Remember, what they do is they swap derivatives.
Now, is that part of the answer that we write it as a radical, or do we need to put it as that?
You can write it as the radical, or you can leave it as the 1/2 power, whichever one you want. You're good either way. Sometimes it's easier to put it back as a radical because raising it to the 1/2 power involves extra parentheses that you don't want to use. It should take it. As long as you get your parentheses in the right place, it should take it. And my math lab is actually pretty good at actually making fractions in the exponents and things like that so that you don't have to have parentheses. Well, I'm not done, so you got it. So then if I'm going to multiply factor 2 times the derivative of factor 1, then I've got to bring this down here. E to the x squared plus 1 times 2x. And you can stop there. There's a lot of parentheses there, but you can stop there. Now, like Miles said, if you wanted to change this and call that the square root of 5x plus 2, you sure can do that. That's fine. You can do the same thing with this, but if you're going to do that, you're probably going to need to drop it down into the denominator because it's got a negative sign in front of it. No, it's not pretty. It is not pretty. Calculus gives ugly answers. Algebra is what makes it look pretty. But it's a lot of work to make it look pretty.
Like polish. But
Algebra is just polish. That's right. Basic algebra we needed to learn. That was why I made you do the skills review of the things I knew you needed to know how to do. But you don't need it to pretty this stuff up. That's not what you need it for. You needed it to remember that you could take a radical and make it into an exponent. To remember that you could multiply out a polynomial and avoid having to do product rules sometimes. Okay? That's okay. Beat away.
Where you multiply the 5 and the 1/2, I did. I'm not going to do it.
No problem. No problem. Okay. Okay. I only did it to avoid having to write an extra set of parentheses. Okay. How about I do this? Oh, that's all right. I don't need it. They go to the trash can when I'm done with them. That's why I record. That's why I record, guys.
Just gonna wonder why we're digging through trash.
I used to save them, but not anymore. Okay, this is a what kind of function, and be careful. Because remember, if it's quotient rule, there has to be variables in the top and the bottom. So is it quotient rule? No. It is not. Okay? But we do, in order to do the problem, we are going to have to rewrite it. Because we don't want to have to deal with this in the denominator. Now, I will tell you a little secret. You could do this as a quotient rule problem. You really can. You can do it as a quotient rule problem. What happens is the derivative of the numerator turns out to be 0, so that it makes some stuff disappear. But it's really easier if you realize that you can take this off the bottom and put it in parentheses and lift it up to the top with a -1 power. Okay? So first thing I'm going to do is rewrite this as 100,000 times the quantity 1 plus 100 e to the negative 0.3 x power, all inside parentheses and raised to the negative 1 power. That way I've made it into a relatively simpler chain rule problem, and I don't have to go taking a whole bunch of derivatives and trying to remember what order to put them in. You could do it as a quotient rule problem, but it's not as easy to do it as a quotient rule problem. So now we're going to take the derivative. What you do with the derivative is you remember that's just a number. It's just a multiplier. It's riding along. Bring it down. Don't change it. Don't mess with it. Bring it down. You're going to need to keep these parentheses. And you're going to need to keep what's inside of them. But that parentheses has a power on it, and that power is negative 1. Multiply it times that number in the front. If it had been negative 2, I would have went ahead and multiplied that and called that negative 200,000, because that way I don't have to keep up with it anymore. Keep what's in the parentheses. I don't even fill it in until I'm done. Keep what's in the parentheses. Then, because I've brought my power down in front and multiplied by it, I'm going to reduce my power by 1, which makes it negative 2. Now, I'm going to keep what was in the parentheses. Didn't do anything with it, didn't change it, kept it just like it was. I just recopied it. What's the derivative of 1? 0. Not writing nothing down if I don't have to. What's the derivative of 100 times e raised to a power? 100e raised to the exact same power. Okay? Remember, you repeat it. When it's e raised to a power, you bring it on forward with the derivative. And then you take the derivative of the power. You're done. Miles says he's not multiplying anything out. That's fine with me. When you're not using e. As long as you've got e, the natural log of e is 1, so it disappears. You're still really using it, but it disappears. Okay? Now, honestly, you think that looks pretty ugly, and it does look pretty ugly, but it don't look anywhere near as ugly as the result of the quotient rule problem if you try to do that. Okay? Some of these do look nasty.
You've actually put it on here.
Yeah. Yeah, I did not put it in there. I did not. Well, actually, let me see. Yeah. I pulled it out because I wasn't going to show it to you, but since you see it in the PowerPoint I posted, that's if you do it using quotient rule. Yeah, I didn't think you'd want to do it that way. I mean, this is equivalent to this. It's exactly the same expression. But you don't want to think about it because it's like, no, it's too many steps. Okay. That's all of our ugly problems. Well, I left this one in here because in business, especially in sales, there is something called the logistic function. And the best way for me to explain to you how a logistic function works is, I want you to think about this. If you have a little island, and the island has all kinds of vegetation on it, and there's plenty of food, and there's no predators, it's just there. But some moron comes and he brings 2 bunnies to the island. Okay, what happens?
The vegetation starts to go down.
Well, assuming that the 2 bunnies are of opposite genders, they multiply. Okay? So very soon the vegetation starts disappearing quickly, and the number of rabbits starts going increasing. But do they increase forever? No. What happens at some point?
The original rabbits.
Well, no, go with them. But
if they leave them there unattended, yeah, they will. I mean, 2 become 4, and 4 becomes 16, and 16 becomes 132 really quickly. Okay? And they eat like little maniacs, and pretty soon there's no more food. So then what happens to the bunnies? They start dying off. And do they die off dead, all of them, and they all go away? No. It's a logistic problem, because what happens is they increase exponentially, but there's what's called a carrying capacity. There will become an equilibrium between the rabbits and the food, so that the amount of food available will limit the number of rabbits that can continue to live on the islands, okay? The same thing happens in business with sales. And we talked about this before, little fidget spinners, okay? Somebody saw one. Oh, isn't that cute? I want one, I want one, I want one, I want one. Oh, my God, I don't care if I ever see one of these again. You know, and they're fizzled. You know, nobody wants one. They reach their carrying capacity. In fact, actually, they didn't really become logistic functions, because at some point they're not making those suckers anymore, and they do drop back down to 0. Okay? They went the way of the Slinkies and the Rubik's Cubes that eventually will come back, but right now nobody's interested.
So let me ask you this: as the number of bunnies die off, does that mean the vegetation starts to come back?
Right. The vegetation comes back, and the bunnies will start to regain, but they will never peak again. They'll do this number for a little while until it flattens. Okay? So they reach a true equilibrium. Mother Nature is really good at reaching true equilibrium if we leave it alone. Okay? That's the reason I left this up here, because that's what goes on with logistic functions. This is what a logistic function looks like. And every one of these letters actually has a value that you can pick out in the problem. So the example I want us to look at is a business example, and that's the only reason I left this one in there, and I probably won't put one on test, to be honest with you.
Thank you.
But I think it's worth looking at, so that if you ever do need to deal with it, you'll remember where you saw it before. A company sells 990 units of a new product in their first year. But in their 4th year, they sold 3,213 of that product. The product apparently was well-liked, and it caught on, and sales increased. They expect that sales can be approximated by a logistic function because they're smart. They realize that their sales are not going to increase exponentially forever. They realize that they're going to saturate the market at some point. So they expect their sales can be approximated by a logistic function, and that they're going to level off at around 100,000 in the long run. So the 100,000 is what I was referring to as the carrying capacity. That's where their sales are going to level out and kind of stay in equilibrium for quite a period of time. the first thing we want to do is find a formula, S of t, for the sales as a function of time, and then find the rate of change in those sales after 4 years. Now, the way that you need to find the formula for S of t is you're going to use the formula for the logistic. And this is what the things in the logistic formula actually represent. Your carrying capacity is M. That's where their sales are going to level out. And the problem says the sales are going to level out at about 100,000. M is the same value that you're going to have here. No, M has to do with the limit that the function is going to reach. It's going to be the leveling out point. The slope on this function is going to change drastically because it's going to start out being positive but relatively shallow, and then it's going to grow until it's relatively steep, and it's going to go very steeply for a while, but then it's going to become less and less positive and start to flatten out and approach zero. Yes. Yes. And then that's going to be multiplied times e raised to this power, and again, the m shows up in the power. Okay? Now, the number k that you see there is a constant, and it is particular to a particular problem. So we're going to have to figure out what k is. T is the only variable in the problem. It's time, because the number of units produced changes over time. G sub 0 is how much they produced in their first year. That's what's called the initial value. Okay? So I'm going to label a few things for you. I said X, but it should be T, as T approaches infinity. That's the long-term limit. That's where they expect it to level out. This is called the initial value. That's their first year's sales. That's the sales in year 0. Okay? That's where they start. The whole growth function is a function in time. So time is your variable. In order to know the complete formula, we have to know what K is. And the way that we figure out what K is because they gave us one more piece of information. When T was equal to 4, the value of the function was equal to 3213. Okay? So what we're going to do is we're going to take this and take into account that when T was equal to 4, let me change that because I've used some red to label things. When T is equal to 4, the value G of 4 was 3213. This is the hardest part of the problem, and it's all, unfortunately, arithmetic. That's really all it is. It's all arithmetic. Because we have to solve this whole mess to figure out what K is. We need to know what K is so that we have a formula that works for all values of T, not just for T equals 4. Okay? That's the hard part. I already printed it out so that I don't have to write it as we go because it looks neater if I print it out in big print. So this is what we've got. In year 4, the formula looks like this, and the result of the formula is 3213. The only thing I did from here to here was I took this 4 and I multiplied it times that 100,000. So that I had one single number that was up there with that K. And if you remember from your long ago algebra classes, the way that you solve an expression like this is you do something called cross multiplication. We're going to cross multiply. That means we're going to say 1 times that, and then we're going to say this times all of that. So 3213 times the denominator is equal to 1 times the numerator. Then we're going to multiply out 3213 times 1 is 3213. And 3213 times 100.01, which, if you're wondering where that came from, is that number right there that we started out with that fraction. So it came from that other arithmetic, times e raised to that negative power. So when we multiply 3213 times that, we get this. I'm going to try not to go too fast because I don't want to lose you. These, incidentally, are in Shelby. So if you don't get everything quite copied down, this whole thing is in Shelby, including this part. Okay.
Yeah, the 2 word problems you've done are the 2.
I've got them up here. I haven't thrown them away. Okay. What I've done in the next step was I subtracted 3213 from both sides. That's what got me here. And then I divided both sides by 321,332, which came from there. So what I have now is that e raised to that power, I've got it down to where all I've got is e raised to the power, is equal to approximately that much. That's all calculator. We're doing all this arithmetic on the calculator. The reason that I wouldn't necessarily ask you to do one like this on a test, although if we had time for a project, I might give you a project like this. But there's only one thing you need to know this for. if you take the natural logarithm of e raised to the power, you know what you get left? The power. Because remember, the natural logarithm of e is 1, okay? Because they're inverses of each other. So all you're left with is the power. There is a process in algebra that says, and you've done this forever, if I add something to both sides, it's okay. Because I added the same thing to both sides. If I subtracted something from both sides, it's okay. Because I subtracted the same thing from both sides. If I multiplied both sides by something, it's okay. Because it was done the same on both sides. Well, logarithms work the same way. If you take the natural logarithm on one side, then you take the natural logarithm on the other side. Taking the natural logarithm of e gets rid of e. So then you take the natural logarithm of the other side, and now this isn't so hard. Because all you need now to do is to divide both sides by that negative 400,000. I'm sorry, not negative, because that actually you do divide it by the negative so that you can get rid of the negative in front of k, because you want to know the value of k itself. So when you do that, your calculator huffs and puffs and gets cranky on you, but it eventually blows out that number right there. Actually, what it spits out is 3e negative 6. Which is equivalent to that little bitty number right there. That's the value of k in our formula. That means this is what our formula looks like. Because when I take this number and I multiply it by 100,000, which was in the formula, that's what I wind up with. So there's your formula. And with that formula, they can predict what their actual production is going to be in any given year. And if they were feeling really ambitious, they could take the derivative of that function and tell whether their production would be increasing quickly, increasing slowly, or maybe leveling off in that year. Because that's what the derivative would tell them, is how are your sales changing as time passes. So I wanted you to see what a logistic function looks like, because there is a whole science in business now called logistics, which has to do with how you move things around the country, how you warehouse things, and how you market and distribute things to make things the most profitable and manage your money the best. There's a whole degree program in logistics and business. Yeah. Yeah, the computer programs take care of stuff like this for us, but it's all, I mean, somebody had to know how to do this to program those computers. Okay? Yeah, I had heard that. So that's as far as we're going with that problem. We're not going to do anything else with it other than we came up with it, except now that we do have it, this says find the rate of change of sales after 4 years. We know what their sales were in year 4. What's going to happen to their sales in the 5th year, basically? Okay? That's what we'd like to know. They'd like to know that too, because obviously their sales have been increasing pretty good, but what's going to happen in the 5th year? Are their sales going to continue to increase, or are they going to start to level off? Well, as it turns out, if you just plug that formula in, you can plug in all the years you want to. Here's that this is what a logistic curve really looks like. Remember, this is where the bunnies first went in? And then they started multiplying, and then more bunnies got old enough to multiply some more, and they grew faster and faster and faster until they reached carrying capacity. Well, that's the same thing that happened with those cells. So what they're asking us, it says the rate of change after 4 years is about 993 units per year. The reason that we say that is because 4 units, about 4 years in, we're talking about the slope of that line right there. What we would do is we would take this function and we would do n deriv, and I would plug that function in y1, and you would find the numerical derivative of that function with all the parentheses necessary to type it in with respect to t, or in the case of the calculator, x, at a value of x equals 4. And it would come back and tell you that it's about 993. I would expect you to actually take that derivative using any of the rules. In applications problems, I want you to learn to use your n derivative function. If you've got the function given to you, you don't have to take the derivative if all you need to know is what's the value of the derivative at some specific number. Okay, now if they ask you for a formula for the rate of change, yeah, you've got to take the derivative. But if they're asking you what is the rate of change at 4 years or at production level of 10,000 units, use n derivative and plug that into the calculator. Because what I want there is I want you to explain to me what that derivative means. What does that tell you about the situation? Because that's what your boss is going to want to know someday. Your boss isn't going to want you to say, well, the rate of change at t equals 7 is, he's going to look at you like you've got two heads and say, what are you talking about? This is not math class. I asked you a question. Answer the question. Okay? And that's what I want you to do, too. I want you to be prepared to answer that question. So at this point, the only thing we have left is the natural logs. And if you look at the natural logs, they very closely mirror what we just looked at for exponential. Everything that you learned is still good. Everything is still there. I wrote the formulas on the board for you, so we're just going to do a couple of examples. I'm not going to beat you up with really tough examples on the test. I will give you some that I think you can pretty well do in 1 or 2 steps and not have to get too complicated. But here is the natural log of 6. That means we're going to follow this formula right here. So if you're taking the natural log of anything, its derivative is 1 over whatever you're taking the natural log of. With the caveat that since 6x is an inside function, you will need to multiply by its derivative. So what is the derivative of 6x? 6. And something very interesting happens. And that always happens. If all you have is the constant multiplier in front of x, it winds up canceling itself out. So 1 over taking the natural log of any number times x winds up being 1 over x. Now, if that x is not just an x, if it's like x squared or something else, then, it doesn't work out quite that nice. But if it's just a number times x, the number winds up canceling itself out. It's always going to turn out to be 1 over x. If you have a log function, that is a base 10 logarithm. That's the only base logarithm I'm ever going to ask you about. Because base 10 are the only ones we ever use in the real world. I don't know I've never run across an application yet in all the work I've done that would ask me about a base 3 logarithm. I've never needed to know that. So these are base 10 logs. That's the one that you don't see anything but log. That's assumed to be 10. So that means that when I do this derivative, that's going to be 1 over x times the log of 10, the natural log of 10. So since this is a base 10 logarithm, then you write it like that. And yes, it does go in the denominator. It cannot go in the numerator. It has to go in the denominator. Do part A first. The natural log of this expression. The derivative of the natural log of anything is 1 over the anything. And then if it's anything but x, you need to take the derivative of anything. And in this case, the derivative of x squared plus 1 is 2x. It's actually 2x plus 0, but we don't need to write down the 0 for the derivative of 1. And Miles, I won't even make you put the 2x in the numerator. You can leave it multiplied out. You don't have to put 2x over x squared plus 1. You can leave it multiplied out. That's okay. All right? Base 2. Some of the examples they use in the book are different bases, but as far as realistic use, they don't work any different. A base 2 logarithm means somewhere in the answer we're going to have to take the natural log of 2. So it's going to be 1 over this. But then down in the denominator with it, you need to take the natural log of 2. And remember, the natural log of 2 is just a number. But then in order to be finished, we're going to actually need to take the derivative of that because that's another expression. So 2 times 3 is 6x to the first power minus 1 times 4 is 4. X to the 1 minus 1 becomes x to the 0 and disappears. So you can leave that way, or you can stack it back up. You can put 6x minus 4 on the top of that, so that you only have one fraction to write. Natural log of whatever the base is, and it follows it to the denominator by the derivative of whatever you were taking the log of. Okay? What about having the natural log of something called the absolute value of 5x? All the absolute value tells you is whatever x is, you plug it in and you take the opposite sign of whatever's in there because absolute value is always positive, right? So we're taking the natural log of the absolute value of 5x. That's going to be 1 over the absolute value of 5x. Just take your absolute value bars with you. Can you take the derivative of 5x?
Yes.
What is it? 5. Now, in that case, once again, the 5s could just cancel out. They, in fact, do. because the 5 doesn't change what the absolute value of x is going to turn out to be. You're still going to multiply x by the number 5 and then have to divide it out again. Or you can leave it just like that. You could make it 1 over the absolute value of x. But there's nothing wrong with leaving it like it is. You still want to keep the absolute value bars, because if you're given that, there's probably a reason for the absolute value bars. It may be some application where, for whatever reason, that your answer always has to come out to be positive. And absolute value ensures that happens, regardless of what value of x you're looking at. Anybody see a product? Yeah, no, yes. Yeah. There is a product here. Okay? This time we actually have a product. So the first thing we do is we take the first factor, 3x, we multiply it times the derivative of the natural log of x squared. And I wrote that step in. You may skip it, but I wrote it in so you'll know why I'm doing the next thing I do. Then I'm going to add it to the natural log of x squared. And I'm going to multiply that times the derivative of 3x. So when I find f prime of x, this is what I'm going to find. The derivative of the natural log of x squared is 1 over x squared times the derivative of x squared, which is 2x, and then I bring back my 3x out here in the front. And then I have the natural log of x squared, with or without the parentheses. If you're doing it on the calculator, it'll make you put the parentheses. And the derivative of 3x is 3. Okay? Cleaning up isn't required, but if you do, it does look a whole lot prettier in this case, because 3x times 2x is 6x squared on the numerator times 1 over x squared plus 3 times the natural log of x squared, and since x squared cancels, prettying it up makes it a little easier to deal with, but there again, you could have quit above that. You didn't have to go that last step. Yeah, I know. If I give you an out, you're going to quit. Okay? But the thing is, I've got to see the step where you actually did the calculus.
Oh, yeah.
That's all I want to see. Anything you do after that, it's nice and it's pretty, and, you know, I'll give you attaboys for it, but you don't have to.
Once I get the routine down, I have no problems. Right now, I'm just trying. It's easier for me to see all that.
Yeah. I understand. Okay, now our last one. Quotient rule. So what's your pleasure? You want to do quotient rule, you want to do product rule? Because you can always turn a quotient rule problem into a product rule if you want to.
Do quotient rule.
Okay. Since it's going to take a little more room, I'm going to get a clean sheet of paper. If I'm going to do it as a quotient rule, I always color code my quotient rules because it's easier for me to figure out what I'm doing when I do that. So here's my numerator. Here's my denominator. So there's the quotient. My denominator is t. The derivative of my denominator is 1. My numerator is that ugly log function, which means it's going to have an ugly derivative. So it's going to be 1 over the natural log of the base, which is 8, times the expression, t to the 3/2 power plus 1, times the derivative of t to the 3/2 power plus 1, which is 3/2 t to the 1/2 power plus 0. Now I'm ready to combine everything. Does everybody know where the derivatives came from? How we got those? So then S prime of t, I always start with the denominator. And I square it. Then I follow through by taking it to the numerator. And I multiply it times that big whole ugly thing. And then I subtract. And I take the numerator, and I multiply it times the derivative of the denominator, which is 1, and promptly disappears. So if you don't write down the 1, that's all well and good. You don't have to. And you don't have to do anything else to it. You have done the calculus. The Chapter 12 test actually is usually a much better test than Chapter 11, because Chapter 11 you're trying to get used to everything. Okay? I'm not going to base it on my last semester's class, because last semester we had a really rough semester, and it was hard to get through with everything. But normally, the worst test generally is the first one. Chapter 12 is usually a lot better. 13 and 14 are still about as good, about the same level as Chapter 12, because it's just doing more of the same, doing more with it. And then everybody kind of freaks out a little bit on Chapter 15 because, and I'll just give you warning right now, Chapter 15, what we do is we take what we're doing now and we go backwards. You have the derivative and you have to go back to what you started with. But just like there is for this, there's formulas for doing it. Okay? So, since you wanted quotient rule, I did it by the quotient rule. We could have done it by product rule, but there's no reason to do it twice. It is late, and the only example I had was the Kelly Blue Book problem. I'll be glad to work that one out for you and post it in the video on Shobi. But you got your practice test, and I think that's more than enough to keep you busy.
And that last one.
You said you were gonna upload the answers.
True. Yeah. Probably. I want to try to get all the rest of these tests graded first, so at least you know what your last test grade was. Because I know you've been waiting on those, and because of everything that's happened with me, I haven't been able to get things done as efficiently as I wanted to. But I will get those done, and I do already actually have the key made out. I just... You too.